So we'll be covering interference of light in this lecture, and this is the second part of the series of lectures dealing with interference of light. We have already covered the topics of coherence, Young double slit experiment, and the criteria of interference of light in the first lecture. So in the second lecture, in the present lecture, we will be dealing with Fresnel's biprism, Llyod's mirror, Newton's ring, and interference in thin films. These are the topics that we are going to discuss in this lecture. We start with Fresnel's biprism. This is a variation of the Young's double slit experiment, and it consists of two prisms which are joined at the bases to form an isosceles triangle. A single wavefront impinges of both the prisms, and at the intersection of the wavefront is reflected right, while the right segment is reflected left. You can see that the wavefront is coming. They are the rays coming out of the prism. If we produce these rays backward, these rays converge at a point. Similarly, these rays converge at this point. So, accordingly, these are the two virtual sources that are created. Now, the purpose of this creating this biprism was that the Young's double slit experiment, we have approximated a slit acts as a point source. But in practicality, since the slits have a finite width, so they can't be treated like a finite source, that a point source. So this kind of a device was designed, and as you can clearly see that these virtual sources can be clearly assumed to be a point source. So in the biprism, while constructing this isosceles triangular biprism, the this angle and this angle are very small, while this angle is an obtuse angle. This angle is about 179 degrees, and these two equal angles are half degree each. So by looking from a distance, you will be able, no, you will not be able to judge. You will not be able to distinguish between the biprism and a simple glass plate. The only small line is visible here. So as this experiment is analogous to the Young's double slit experiment, so all the formula that were valid in the Young double slit experiments are also valid in this case, and with a minor exception that here the distance between the virtual sources cannot be measured directly because we are not creating them, they are being created automatically. So what we do, we place a converging lens between the biprism and the screen, and forming the real images of the virtual slits on the screen, we measure the distances separately for both the sources. The distances are D1 and D2. And the distance between the two virtual sources is square root of the multiplication of D1 and D2. So this is a biprism. This is a screen. When light comes from the source on the biprism, the center line goes undeviated, while the lights in the upper rays in the upper portion are converged towards downwards, and the rays in the down are converged upwards. You can see. by this side. So this area, these are coming down, these rays are going up, the center ray is going straight. So this is the region formed between the rays coming from the virtual source V1 and V2. So the interference pattern is formed in that way. Second device is the Llyod smirror, which was described by Llyod in 1834. Its original goal was to provide further evidence for the wave nature of light. So this is an arrangement for producing an interference pattern with a single light source. So waves reach at a point P either directly from the source S or after reflection by a plane mirror. Since the image of this source is formed behind the mirror, and when we extend this reflected light, we see that these two meet at the point S dash, which is the virtual source. So light coming from this original source S and the virtual source S dash is made to interfere at the point P on the screen. So this can be thought of as a double slit source with the distance between the point S and S dash comparable to the distance small d, that is the distance between the virtual sources. The positions of the dark and the bright fringes are reversed relative to the pattern of the two real sources, because on the after reflection there is a phase change of 180-degree introduced, because the light is getting reflected from the denser medium. So if the light is reflected from any denser medium, there is a phase change of 180 degree. So an electromagnetic wave undergoes a phase change of 180 degree upon reflection from a medium of higher refractive index, analogous to a pulse on a string reflected from a rigid support. You can see. And there is no phase change when the wave is reflected from a boundary leading to a medium of the lower refractive index. When the reflection is from the boundary of a lower, since here is the lower refractive index, the wave is coming in from in the denser medium, it is getting reflected inside the denser medium from the rarer medium. So there will be no change in the phase. And the most common application of the rod mirror is in the UV photolithography and nano patterning. So if one wishes to create a series of closely spaced interference fringes using a double slit interferometer, the spacing between the virtual sources and the slit must be increased. Increasing the slit spacing, however, requires that the input beam be broadened to cover both sides. So this results in the loss of power. In contrast, increasing the distance between the virtual sources in the Llyod mirror technique does not result in any power loss, since the second slit is just reflected virtual image of the source. Hence, the Llyod mirrors enables the generation of a finitely detailed interference pattern of sufficient brightness. Now we discuss another device called the Newton's ring. This is another method for viewing interference which takes place in a film which is created between the surface of the plano-convex lens and a flat glass surface. This. The air film between the glass surfaces varies in thickness from 0 at the point of contact to some thickness small t. When a parallel beam of monochromatic light is incident, normally on the combination of a plano-convex lens and a glass plate G, a part of the incident ray is reflected from the lower surface of the lens, and a part after refraction through the air film between the lens and the plate. The part is reflected from this surface, and the part travels further and is reflected from this glass. So these are the two virtual sources. And these two light interfere and give the interference pattern, which is observed. These two reflected rays are coherent, hence they interfere and produce a system of alternate dark and bright fringes. Since this is a lens and lens is circular in shape, so the fringes are also circular in shape. And these circular fringes are called Newton's rings. So for a normal incidence of the monochromatic light, path difference between the reflected rays is nearly equal to 2 mu t, where mu and t are the refractive index and thickness of the air film respectively. The fact that the wave is reflected from air to glass surface introduces a phase change of pi. Therefore, for bright fringe, this path difference 2 mu t is equal to an odd multiple of lambda. And for the dark fringe, this is path difference is equal to an even multiple of lambda. And from this figure, this is the sphere of which the lens is a part. This is the circular fringe. Sorry. So this is the diameter of the nth ring. And from this figure, we deduce that dn square by 4 plus r minus t square is equal to r square. T is this distance. So on neglecting this t square, we arrive at this relation. And now from the equations for the nth and the n plus mth bright ring, we take two rings, nth ring and the n plus mth ring. The diameters of both the rings will be these. And then we subtract. These are the diameters for the nth and n plus mth dark ring. So when we subtract the diameters of the n plus mth ring and the nth ring, and we after simplification we arrive at the expression for the radius. Since we have the air film between the lens and the glass plate for which the refractive index is 1, so this relation reduces to. So if we know the radius of curvature of the lens and calculate the diameter of the nth ring and the n plus mth ring, and from that we will be knowing what is the difference between, like this is the fourth ring and this is the sixth ring. So m will be equal to 6 minus 4, that is 2. So m will be 2. We can find wavelength of light. So in the experiment that we do in the lab, we can find the diameter of various rings, and using those diameters and the known value of the radius of curvature of the lens that we have taken, we calculate wavelength of light from this formula. This is the apparatus for the Newton's ring. This is the glass plate. Light enters from this lens. Part is reflected from the glass plate, and there is a convex lens. This is the moving microscope. This is the light is coming from this direction, reflected downwards. This is the convex lens placed here on and a glass plate downwards. Light is reflected from both the surfaces, and the interference pattern is observed from this microscope. Now we see the phenomena of the interference in thin films, which is a commonly observable phenomena in soap bubble, in pool of water. Whenever we see there is a rainbow coming in soap bubble and all, that is due to the interference of light. And thin film interference is the phenomena that is the result of light wave being reflected off it through surfaces that are at a distance comparable to its wavelength. So the thickness of the film should be order of the wavelength of light. If there is a very thick film, then there will be no interference. So in principle, how this takes place? When a beam of light is incident on a surface of a film, it is reflected from the upper surface. Part of it is transmitted inside the medium by refraction, and this transmitted light is again reflected from the second surface, and some of it is transmitted outside the film. So this reflected light from the second surface comes back to the upper surface and is transmitted. Part of it is transmitted and the rest is reflected. We are not concerned with that. So these two reflected lights, one from the upper surface, other from the lower surface, interfere and produce a interference pattern here. So we need to calculate the path differences between the two lights. This is the incident ray, which is part of it is reflected, other is transmitted, which is reflected from the other lower edge of the film, lower surface of the film, and is reflected from the lower surface, comes to the upper surface, and is transmitted back into the medium. We need to calculate the path difference. So the path difference will be, first we should see how much path this ray has traveled, which was transmitted. It has traveled path AB and path BC. So the path traveled in the denser medium is AB plus BC multiplied by the index of refraction of the denser medium. The path traveled by the ray directly refracted from the first medium is AD. So the path difference will be equal to mu times AB plus BC minus AD. Now from the geometry, we get AE is equal to EF since these triangles are congruent. BC is equal to BF and AB is equal to BF because these two triangles are congruent. How you can see these are the two 90-degree angles. This side is common. This angle is equal. These two triangles are congruent. So if we consider triangle ACD, this is angle of incidence. The sine of angle of incidence is equal to AD upon AC. And in triangle AGC, the sine of angle of R is equal to GC upon AC. So we divide these two. Sine I by sine R is equal to AD upon AC. And sine I by sine R is equal to mu. So AD is equal to mu into GC. Now see, we see this path difference. Path difference is mu into AB plus BC minus AD. So we substitute the value of AD as mu GC and we combine all the terms. So we get this one. So this is the path difference. Now this AB is equal to BF and BC is equal. As such, we substitute AB is equal to BF. And BF plus BC. BF plus BC is FC. So the path difference is mu into FC minus GC. FC minus GC is FC minus GC. FC minus GC is what? FG. So the part difference now become mu into FG. Now we consider the triangle AFG. This is angle R. So cos R will be equal to FG upon AF. So from this relation, FG is equal to AF into cos R. If we substitute, AF is equal to AE plus EF. These two, AE plus. This is equal to the thickness of the film. So this is also equal to thickness of the film. This is T plus T. So AF is equal to 2T. So the path difference is mu FG, which is now equal to FG is 2T cos R. So now the path difference is 2 mu T cos R. This path difference produces constructive interference when this is an odd multiple of lambda by 2 and produces destructive interference when this is an even multiple of lambda by 2. This is the case of the reflected light. And when we consider interference between the transmitted light, the light which is transmitted after first transmittance and this light, interference is taking place between these two lights. The path difference will be same between the two transmitted lights, but the condition will be opposite. For the constructive interference, it should be an even multiple of lambda, and for destructive, it should be an odd multiple of lambda. So the interference depends on, see the what are the quantities involved: lambda, mu, T, cos, and R. Wavelength, refractive index, thickness, and angle. So the wavelength and angle of the incidence, the thickness of the film, and the refractive indexes of the materials on either side of the film. These are the quantities on which the interference depends. These are the references that we have consulted. And for the remaining topics of interference, like Fevre-Perret interferometer and Michelson interferometer, I've already discussed it with you beforehand, and the videos are already available on the channel. So I thank you for a patient listening, and request all of you to subscribe to the channel, and you can put your questions in the comment box with your email address so that I can reply to your comment.